In this video, we're going to talk about two important concepts: internal energy and enthalpy. So internal energy is pretty straightforward. This is just the name that we give to the total amount of energy that a substance possesses. And the symbol we use to represent internal energy is U. In some other textbooks, sometimes you'll see it abbreviated E, but in our textbook, we'll use U. Now, it turns out the total internal energy that something has is actually very hard to determine. Right? If we imagine a molecule and try to determine the internal energy of that molecule, well, we have to consider what is all of the energy associated with holding all of the electrons to all of the nuclei. And then we have to consider all of the energy of the different bonds that the molecule may have. And then if the molecule is rotating and vibrating and translating, we have to consider all of those energies. And that doesn't even include the energy of the nuclei themselves. So what is the energy that holds the protons and the neutrons together? And protons and neutrons aren't fundamental particles. They're made of quarks. And so we have to consider the energy that holds the quarks together in protons and neutrons. And so actually determining the total internal energy that something has is pretty challenging. And in chemistry, oftentimes knowing the total energy isn't even that useful to us. But what is useful to us and is much easier to determine is changes in internal energy. So when I have a chemical reaction, how does the internal energy change? And so instead of looking at U, we're often talking about delta U. So what is the change in internal energy for a given process? And whenever we have a chemical or physical process, the way we exchange energy is through heat and work. And so the change in internal energy for any process is equal to the heat and the work that are being exchanged. And we've talked about the law of conservation of energy, that energy cannot be created or destroyed, just converted from one form into another. Another way to say that is the first law of thermodynamics. And the first law of thermodynamics tells us that the change in internal energy for the universe is zero. So that doesn't mean that the internal energy for a particular system can't change. It's just that whatever happens to the system, essentially the opposite has to happen to the surroundings. Right? So if I take this equation and rearrange it, I could also write that delta U of the system is equal to minus delta U of the surroundings. And we've kind of already used this in calorimetry. Right? In calorimetry, whatever heat was lost by the system was gained by the surroundings and vice versa. And so the same thing is true for internal energy in general. If the system gains internal energy, then the surroundings must have lost that internal energy because we can't create and destroy it. It has to be conserved. Now, as chemists, when we're talking about the change in internal energy, we almost always take the point of view of the system. And so on that last slide, we specifically labeled the delta U as either being for the universe or the system or the surroundings. Very often when we say delta U, we mean the system, but we leave that subscript off. So unless we specify otherwise, if you see delta U, we mean the delta U of the system. We often just leave the system subscript off. And so we might just say delta U. And so energy can be transported into the system. This results in an increase in internal energy. So delta U for the system, or just delta U, would be positive. And so this can happen when the system absorbs heat from the surroundings or when the surroundings do work on the system. And so a way to think about the surroundings doing work on the system, what we often use to explain that is a piston, right? Where I have a gas trapped inside here, trapped inside a cylinder, and then I have a piston that I can use to either push down on the gas or to raise it up to relieve the pressure on the gas. In order to make this compression happen, I would have to exert a force on the piston to push it down and compress the gas. And so if the gas is what we're defining as our system, then compressing the gas, if the gas is the system, it's the surroundings that are doing work. It's the surroundings that's pushing on that piston. And so in that case, the surroundings are doing work on the system, and so the work for the gas would be positive. On the other hand, if we have the gas under high pressure and we allow the gas to push the piston up, that in that case the system, the gas, is doing work on the surroundings, and so that would be a negative work. The system would be losing internal energy in that case. And then, of course, another way that the system can lose internal energy is if it releases heat to the surroundings. Right, at this time, it's important to introduce the idea of what's called a state function. And so a state function is any property that only depends on the current state of the system. Right, so it doesn't matter how we got there, it just matters what the current state is. And a lot of the variables that we've talked about are examples of state functions. So pressure, volume, temperature, internal energy, and things that we'll talk about going forward, enthalpy, entropy, and free energy. These are all examples of state functions. Path functions, these are variables that do depend on the path. It does matter how we got there. And two examples of those are work and heat. And so let me give an example to try to explain the difference between state functions and path functions. So I have here a picture of the Empire State Building, right? And so it's 100 stories, but if we were talking about our distance from the ground, right? So if we were up here in the top of the Empire State Building, our distance off the ground doesn't matter how we got there. Right, so if you imagine that we all took a trip to the Empire State Building, and I took the elevator, and I made you guys take the stairs, right? Once we got to the top, our distance from the ground is a state function. It doesn't matter how we got there, our distance from the ground is the same. But the work that we used to get there is very different, right? I took the elevator, I did very little work, right? You took the stairs, you did a lot of work. So work is an example of a path function. It matters how we get from, in this case, the ground to the top. And so work and heat are the two path functions that we're going to deal with the most, and probably the only path functions that you may encounter in your study of chemistry. Many of the other variables that we've dealt with already and will in the future are examples of state functions. They don't matter how we got there. Pressure doesn't matter how we got to the pressure we're at. It just matters what is the pressure now. Same thing for volume, temperature, and internal energy. And so it can make determining and working with state functions oftentimes easier than working with path functions. And one thing that we're very interested in chemistry is the heat of a reaction, how much heat is being exchanged. But that can be problematic to calculate and determine because heat is a path function. All right, so this brings us to a really important concept in chemistry, and that is the concept of enthalpy. And so I mentioned that very often we're interested in the heat of a reaction, but that's problematic because heat is a path function, and so the heat can be difficult to determine. That's where enthalpy comes in. As we're going to see, enthalpy is very closely related to the heat of a reaction, but enthalpy is a state function. So the formal definition for enthalpy, we use H to represent enthalpy, and it's the sum of the internal energy plus the product of the pressure and the volume. So that may seem like a weird definition, but we're going to see why we use enthalpy. So many of the chemical and biological reactions that we're interested in take place under conditions of constant pressure. And I'm not going to go through the derivation, but if you're interested, ask me in class and I'll be happy to talk more about it. But it turns out that if the pressure is constant, which it is for many chemical and biological reactions that we're interested in, it turns out that the enthalpy will be equal to the heat. And so we can think about the enthalpy as being the heat of the reaction, but it's a state function, and so it's much easier to determine than just the heat is. And so when we talk about enthalpy, two terms that we always use are exothermic and endothermic. And this is related to whether or not the reaction gives off heat or absorbs heat from the surroundings. So in an exothermic process, the system, which is generally the chemical reaction, gives off heat to the surroundings, and so the change in enthalpy, delta H, is going to be negative. It's going to be less than zero. And so combustion is an example of an exothermic process, right? When we put our hands near a flame, we feel warmth because that combustion reaction is giving off heat that we are then absorbing. In an endothermic process, the system absorbs heat from the surroundings. So if you've ever used one of those instant cold packs, you usually sort of smack those, and then it breaks a smaller bag inside the bigger bag that starts a chemical reaction. That chemical reaction is endothermic, and the reason the cold packs feel cold to us is because, being an endothermic reaction, it's absorbing heat from the surroundings. We are the surroundings, so that chemical reaction is absorbing heat from us, and therefore it feels cold to us. So we are often very interested in the heat given off or absorbed by a chemical reaction. And when I combine information about the chemical reaction and the energy, or the enthalpy, we sometimes call that a thermochemical equation. And it looks just like all the other chemical reactions that we've done. It's just that in addition to the chemical reaction, we also state the enthalpy change of that reaction. And so in this case, the delta H, the enthalpy, is negative 572 kilojoules. And so, being negative, this tells me that this is an exothermic reaction. That reaction would give off heat to the surroundings. And the magnitude of delta H tells us how much heat is given off. So a bigger value here means the reaction is giving off more heat. A smaller value here would be a reaction giving off less heat, or absorbing in the case of a positive delta H. So one question that you may ask is, when we have a chemical reaction, if it's giving off heat, where is that heat coming from? Well, the source of the energy, the source of the heat, is the potential energy stored in chemical bonds. And so there's a certain amount of energy stored in any chemical bond. In order to break that chemical bond, I have to put energy into the system. It turns out when I make new chemical bonds, that gives off energy. And so in any chemical reaction, I'm breaking and making chemical bonds. And so then there's sort of a competition. For every bond that I break, I have to put in energy. For every bond that I make, I get out energy. And different bonds require different amounts of energy to break them, or they give off different amounts of energy when we make them. And so all the different chemical bonds that I'm making and breaking combine together, and then there's going to be a net difference in the energy that is required for that reaction. If I end up getting more energy out of the new bonds that I make than I had to put in to break the old bonds, then that's going to be an exothermic process. Right? The reaction is going to have excess energy that it's going to give off in the form of heat. Conversely, for an endothermic process, the energy required to break the bonds is more than the energy that I get out from making new ones, and so the net effect is that energy has to be put into the system to make that reaction happen. Now, very often we like to represent the change in enthalpy of a chemical reaction graphically. And we do that in what's called reaction energy diagrams. And so if we were going to draw a qualitative reaction energy diagram for this chemical reaction, I can see that the delta H is negative. So this is an exothermic process. And so what a reaction energy diagram looks like is, on the x-axis, we plot what's called the reaction progress. And kind of think about that as being time. And on the y-axis, we plot the enthalpy. We could also plot the internal energy, but very often it's the enthalpy that we're plotting. And so for an exothermic process, right, sort of in the beginning of the reaction, I have, this is not true just true for an exothermic reaction, for any reaction, right, at the beginning of the reaction I have the reactants, at the end of the reaction I have the products. And so we represent the change in enthalpy. Now for an exothermic process, where delta H is negative, the reaction is giving off enthalpy. So it's losing enthalpy. The products are going to have less enthalpy than the reactants. And so I could represent that by plotting the energy, or the enthalpy in this case, of the reactants, and then I'd want to draw the products lower because they have less enthalpy in the case of an exothermic reaction. And so then the difference in enthalpy between the reactants and products, this is my delta H. So in this case, that would be negative 2043.9 kilojoules. Now I think our book at this point leaves the reaction energy diagrams as being drawn like this. I usually like to add in one additional thing, and it's something that we'll talk more about next semester, but that's the idea of activation energy. So most chemical reactions require us to put a little bit of energy in just to get them started, or a little bit of enthalpy in just to get them started. And so if we were to plot what that looked like as the reaction progressed, we would see that there's actually a barrier in between the reactants and the products. And that represents the energy that we had to put in. And so this energy that we had to put in to get the reaction going, that's called the activation energy. And as an example of activation energy, if you imagine if we had a bucket of gasoline sitting on the ground, we know that gasoline is combustible. It can react with oxygen in the air, and that is an exothermic reaction. It will give off a lot of heat. But if the bucket's just sitting there and we don't do anything to it, the gasoline's not going to start burning. And that's because it requires us to put in a little bit of activation energy. We have to give it a little push in terms of activation energy to sort of get it over this hump to get the reaction going. And so if we take a match, light it, and throw it into the bucket of gasoline, right, then it's going to burst into flames. And so that match provided the required activation energy to get that process started. Alright, so we drew a reaction energy diagram for an exothermic reaction. Let's see what an endothermic reaction would look like, right? So in this case, delta H is positive. So we'll have the same axes. We have the reaction progress. And enthalpy on the y-axis. Now in this case, in an endothermic process, the system, the reaction, is absorbing enthalpy from the surroundings, absorbing heat from the surroundings. And so in this case, the products are going to have more enthalpy than the reactants. So if I draw the reactants down here, the products should have more enthalpy, right? And now the enthalpy, the change in enthalpy, delta H, is going to be positive, right? Whenever we do changes, it's always final minus the initial, so it's products minus the reactants. When I take the enthalpy of the products and subtract that from the reactants, I'm going to have a positive delta H. But just like exothermic reactions, most endothermic reactions also have an activation energy. And that activation energy is always going to be higher than the energy of the reactants or the products. And so what that would look like in this case, if I was to include drawing the activation energy as the reaction progressed, it might look something like that. So we have an even bigger hump to go to before we get to the products. And so for now, we'll just be drawing reaction energy diagrams qualitatively, but you'll want to be able to, if I give you an exothermic reaction or an endothermic reaction, you'll want to be able to draw an approximate reaction energy diagram to represent that.